All right, so we just went over a lot of information about going over gizmo and object orientation. And as a beginner, it can be tough to make sense of world space and local space and how they differ. Let's first take a look at world space and what that means in the context of our scene. The world origin point is in the center of our scene and is located at 0, meaning 0 in the x-axis, 0 in the y-axis, and 0 in the z-axis. The red line here represents the x-axis. Any value to the right of the origin are in the positive direction, and all values to the left are negative values. The green line is the y-axis. From this view, the values moving away from us are positive, and the values coming towards us are in the negative. And then we have the z-axis, which is hidden from perspective views by default, but we can turn that on in the viewport overlays here. Once clicked on, we can see the blue line running up and down our screen representing the z-axis. All values going up are positive, and all values going down are negative. These axes are your world or global space and will never move. While working around in the viewport, it can be pretty easy to get lost in your orientation to the world, and that's how this navigation gizmo comes in handy. The red, green, and blue lines match with the X, Y, and Z axes in the viewport. And then the line with the letter in it shows which direction is the positive for that axis. Now let's take a look at local space, which is also known as object space. Every object has an origin. It is this little orange dot located here in the middle of our object. Now it's not always located in the middle of the object, but in this circumstance it is. It's located at 0, it's not rotated, and has a scale of 1 across all three axes. These channels are represented in local space, meaning these values are relative to the object's parent. If an object doesn't have a parent, like this object, it can be considered a child to the world. We can see this visually as the axes all line up perfectly with the world here. Now it's important to note that the world is a coordinate system and it cannot be altered, but the children within that system can. Let's take a look at a practical example of this. If we move this object by 1 in the X, Y, and Z, we can see in the channels here, this is now where this object resides in space from the world origin. Now let's add some rotation to the object. We'll add some random rotation here in the X, Y, and Z. So now it's facing entirely differently, as you can see with our move gizmo turned on here. But see what happens now that we try to adjust this object in its Z axes. Notice how its location is moving on all three axes. This is because when we add rotation, we are only changing the direction of an object. We are not changing the coordinate system it resides in. As you can see, if we go in and change the Z transform, it only moves up and down relative to the world. So when we're adding transforms to an object, we're not making changes to the coordinate system, but transforming the object itself. Now let's take a look at parenting, where the coordinate system can move. As you can see in this example, we have a small monkey head, and it's a child of the cube here, which would be called the parent. The cube is set to 0, with no rotation and a scale of 1 across the axes. If we take a look at the child, we can see it's set to 1 in the X, 0 in the Y, and 1 in the Z. Now let's take the cube and translate it and add a bit of rotation. When we select our monkey again, we can see the values of the monkey have not changed. Now notice if we take the monkey head and move it along the Z-axis, you'll notice that this time it only moves in the Z-axis, unlike our previous example. This is because the monkey transforms are relative to the coordinate system created by the parent. So when a parent is transformed, the child must follow along with it. However, the child can move independently from their parent.